Hey everyone! Tonight we're diving into something that'll completely change how you think about life on Earth. When most people hear mass extinction, their minds immediately jump to that famous asteroid that wiped out the dinosaurs 66 million years ago. Giant space rock, massive explosion, goodbye T-Rex. It's dramatic, it's cinematic, and honestly, it makes for great movie plots. But here's the thing that's going to blow your mind. That asteroid event, it's actually the exception, not the rule. What if I told you that life on this planet has been nearly wiped out not once, not twice, but 5 separate times throughout Earth's history? And 4 of those catastrophes had absolutely nothing to do with anything falling from space. No cosmic impacts, no Hollywood-style meteor strikes, just Earth itself, turning against the very life it had nurtured for millions of years. And some of these extinction events were so devastating, so complete in their destruction, that they make the dinosaur extinction look like a minor inconvenience. Tonight, we're going to explore the most terrifying truth about our planet's history. Earth doesn't need help from outer space to become a death trap. It's perfectly capable of orchestrating its own apocalypses, and it's done so with a creativity and brutality that would make any disaster movie director jealous. We're talking about volcanic eruptions so massive, they literally changed the chemistry of the atmosphere, ice ages that froze entire continents, and ocean chemistry shifts that turned the seas into toxic wastelands where nothing could survive. Before we go any further, take a moment to like this video if you're ready to have your understanding of Earth's history completely turned upside down. And let me know in the comments where you're watching from and what time it is for you. It's always fascinating to see who's joining us for these journeys into deep time. Now, grab something warm to drink, dim the lights, and let's travel back through hundreds of millions of years to witness the moments when life on Earth came terrifyingly close to ending forever. The story begins with a number that should terrify anyone who truly understands what it means. 5. 5 times in the last 500 million years, life on Earth has been pushed to the very edge of complete extinction. Scientists call these events the Big 5 mass extinctions, and they serve as stark reminders that our planet's history is written in the fossil remains of species that couldn't adapt fast enough to survive. But here's where the conventional wisdom starts to crumble. When researchers began studying these extinction events in detail, they discovered something remarkable and deeply unsettling. Only one of these 5 catastrophic die-offs could be definitively linked to an asteroid impact. The other 4, they were homegrown disasters, born from the very geological and atmospheric processes that normally sustain life on Earth. This revelation forces us to confront an uncomfortable truth about our planet. Earth isn't just a passive stage where life plays out its evolutionary drama. It's an active participant, capable of both nurturing and destroying life with equal efficiency. The same volcanic activity that created fertile soils and released essential gases into the atmosphere could also pump out enough poison to kill 90% of all living things. The same climate systems that regulate temperature and rainfall could shift so dramatically that entire ecosystems would collapse in geological instants. To understand how Earth became its own worst enemy, we need to travel back 252 million years to witness the most devastating catastrophe in the planet's history. Scientists call it the Permian-Triassic extinction event, but it has a more ominous nickname that perfectly captures its scope and horror: the Great Dying. Imagine, if you can, a world where 96% of all marine species simply vanish. Picture vast oceans that once teemed with trilobites, brachiopods, and countless other creatures becoming nearly empty graveyards. Envision forests and plains where 70% of all land animals disappeared, leaving behind ecosystems so devastated that it would take millions of years for life to recover. This wasn't gradual decline over millions of years. This was catastrophe compressed into what geologists call An instant, a period so brief that it barely registers in the rock record. The Great Dying represents life's closest brush with complete extinction. Never before or since has our planet come so close to becoming a sterile rock floating through space. And the cause of this near-total annihilation wasn't some cosmic accident. It was volcanism on a scale that defies comprehension. In what is now Siberia, something began stirring deep beneath the Earth's crust around 252 million years ago. Not just any volcanic activity, but what scientists now recognize as the largest continental volcanic event in Earth's entire history. They call it the Siberian Traps, and that name doesn't do justice to the monster that was awakening. Picture an area roughly the size of Europe beginning to bleed molten rock. Not through a single volcano, but through countless fissures and vents spread across millions of square kilometers. This wasn't the kind of eruption you see on nature documentaries, with a single cone spewing lava and ash. This was flood basalt volcanism, where the Earth's crust essentially split open and began hemorrhaging magma at rates that challenged the very concept of what volcanism could be. For hundreds of thousands of years, the Siberian Traps vomited forth an estimated 4 million cubic kilometers of basalt. To put that in perspective, that's enough molten rock to bury the entire continental United States under a layer nearly 400 meters thick. But the lava itself wasn't the primary killer. It was everything else that came with it. As these massive eruptions continued relentlessly, they began pumping unprecedented amounts of greenhouse gases into the atmosphere. Carbon dioxide poured out in quantities that made the molten rock seem almost incidental. But the Siberian Traps had a secret weapon that made them far more deadly than typical volcanic eruptions. The magma wasn't just flowing over empty rock, it was burning its way through some of the largest coal and organic deposits on the planet. Picture this hellish scenario. Molten rock at temperatures exceeding 1,000 degrees Celsius encounters vast underground coal seams and organic-rich sediments. The result was spontaneous combustion on a continental scale. Not only were the volcanoes releasing their own gases, but they were also setting fire to enormous quantities of stored carbon that had been locked away in the Earth's crust for millions of years. This created a feedback loop of destruction that amplified the catastrophe beyond anything the planet had ever experienced. The burning coal released even more carbon dioxide, along with toxic compounds that poisoned both the atmosphere and the oceans. The volcanic aerosols and ash-blocked sunlight, causing initial cooling, but the massive greenhouse gas emissions soon overwhelmed any cooling effects and sent global temperatures soaring. Advanced geochronological techniques have now pinned down the timing with terrifying precision. The Siberian Traps erupted at exactly the right time and for exactly the right duration to have triggered the Great Dying. About 2/3 of the magma was erupted before and during the mass extinction period. The remaining third continued to pour out for another 500,000 years after the extinction event ended, as if the Earth was making absolutely sure that nothing could recover quickly. But the volcanic emissions weren't random. They occurred in distinct pulses, each one corresponding to a surge in atmospheric carbon dioxide levels. At their peak, these emissions were happening at rates that rival modern human carbon emissions, pumping greenhouse gases into the atmosphere at a rate of 4.5 billion tons of carbon per year. To put this in context, atmospheric carbon dioxide levels increased 13 times above pre-extinction levels, transforming Earth's climate into something almost unrecognizable. The consequences were swift and merciless. Ocean temperatures rose dramatically, making vast areas of the seas uninhabitable for most marine life. The chemistry of seawater changed as it absorbed enormous quantities of carbon dioxide, becoming increasingly acidic. This ocean acidification made it impossible for creatures with shells or skeletons to survive, as their calcium carbonate structures simply dissolved in the increasingly hostile waters. But perhaps the most insidious killer was one that remained hidden for millions of years until modern scientists detected its signature in the rock record. The Siberian traps weren't just releasing carbon dioxide and sulfur compounds. They were also pumping massive quantities of nickel into the atmosphere and oceans. Nickel might seem like an unlikely villain in this story of planetary catastrophe, but its effects were devastating in ways that wouldn't become clear until researchers began studying the geochemistry of extinction boundary rocks. This toxic metal was carried by aerosol particles from the volcanic eruptions and deposited throughout the world's oceans, where it dramatically altered marine chemistry. Here's where the story takes an even more sinister turn. Nickel is an essential trace metal for many organisms, but the massive increase in nickel abundance triggered an explosion in the population of methanogens, microorganisms that produce methane gas as a byproduct of their metabolism. Under normal circumstances, these methane-producing microbes play important ecological roles. But when their populations exploded due to the nickel influx, they began producing methane at unprecedented rates. Methane is a greenhouse gas far more potent than carbon dioxide, and its sudden appearance in massive quantities sent Earth's climate system into complete chaos. The additional warming from methane made an already catastrophic situation even worse, while simultaneously making life impossible for oxygen-dependent organisms. The oceans became increasingly anoxic as warm water holds less dissolved oxygen, creating vast dead zones where nothing could survive. The precision timing of this catastrophe has been confirmed through isotope analysis and advanced dating techniques. When scientists compared the geological evidence to results from Earth system models, they found that massive and rapid volcanic carbon dioxide emissions during the Siberian Traps volcanism were the most likely trigger for both the carbon isotope changes preserved in rocks and the severe mass extinction that followed. What makes the Great Dying so terrifying isn't just its scale, but its speed. This wasn't a gradual decline that gave life time to adapt. This was environmental collapse compressed into a geological instant, a planetary emergency that unfolded faster than evolution could respond. In less than 100,000 years, a period that barely registers in the geological record, Earth transformed from a thriving biosphere into a nearly sterile wasteland. The recovery took millions of years. The few species that survived found themselves in a world so alien and hostile that entirely new evolutionary pathways had to emerge. The dominance of certain groups ended forever, while others that had been minor players suddenly found themselves inheriting a devastated planet. The Great Dying represents the ultimate example of how Earth's own geological processes can become instruments of mass destruction, requiring no assistance from outer space to bring life to the very edge of extinction. This catastrophe set the stage for understanding that our planet's history is punctuated not by cosmic accidents, but by the periodic unleashing of forces that originate deep within the Earth itself. The Siberian Traps proved that sometimes the greatest threat to life comes not from above, but from below. But the Great Dying was just the beginning of Earth's demonstrations of self-destruction. As devastating as the Permian extinction was, it represents only one method by which our planet can orchestrate biological catastrophe. Earth's geological processes are remarkably creative when it comes to ending life, and each of the remaining mass extinctions reveals entirely different mechanisms of planetary homicide. Travel forward in time to 445 million years ago to witness something that might seem impossible. A mass extinction caused not by fire and brimstone, but by ice and cold. The late Ordovician extinction event stands as a stark reminder that Earth can kill just as efficiently by freezing as it can by burning. During the Ordovician period, our planet looked nothing like the world we know today. Most of the continental land masses were clustered together in the southern hemisphere, forming a supercontinent called Gondwana. The climate was dramatically different too, warm and humid across most of the planet, with sea levels much higher than today. Vast, shallow seas covered enormous areas of the continents, creating perfect habitats for an explosion of marine life. These ancient oceans teemed with creatures that would seem alien to modern eyes. Trilobites scuttled across the sea floor in countless varieties, some no bigger than coins, others growing to the size of serving platters. Brachiopods filtered nutrients from the water in massive reef-like communities. Primitive corals built the first major reef systems in Earth's history. Crinoids swayed in the currents like underwater forests, their flower-like crowns creating gardens of stone that stretched for hundreds of kilometers. But this warm, life-friendly world was about to encounter a climate shift so severe and so rapid that it would eliminate 61% of all marine species in what geologists recognize as the first of the Big Five mass extinctions. The trigger was glaciation, but not just any ice age. This was one of the most severe glacial episodes in Earth's entire history, made all the more devastating because it struck a biosphere that had evolved under consistently warm conditions for millions of years. The speed and intensity of this climate change caught life completely unprepared. Here's what made this extinction so uniquely destructive. The supercontinent Gondwana was positioned directly over the South Pole, creating the perfect conditions for massive ice sheet formation. As global temperatures began to drop, ice began accumulating on this polar landmass at an unprecedented rate. Within a relatively short geological time span, enormous glaciers spread across millions of square kilometers, locking up staggering quantities of water. The effects were immediate and catastrophic. As more and more water became trapped in ice sheets, global sea levels plummeted by an estimated 100 meters. To understand the scale of this drop, imagine every coastal area on Earth today suddenly finding itself 100 meters inland. But in the Ordovician, the impact was far more severe because so much of the planet's habitable area consisted of shallow seas covering the continents. These epicontinental seas were the nurseries of Ordovician life. When sea levels fell, these vast underwater territories simply disappeared, taking their entire ecosystems with them. It wasn't just a matter of organisms moving to deeper water. These shallow sea environments had no deeper water equivalent. They were unique habitats that vanished completely when the water drained away. But the habitat loss was only part of the story. The cooling climate created a cascade of environmental changes that proved deadly, even for organisms that didn't lose their homes to falling sea levels. Most of the marine life in the Ordovician had evolved in tropical or subtropical conditions. These creatures had no experience with cold water, no evolutionary adaptations for surviving in the frigid conditions that accompanied the glaciation. As ice sheets expanded and global temperatures dropped by an estimated 10 degrees Celsius, the warm water zones that had supported most marine life contracted dramatically. The polar front, the boundary between cold polar waters and warmer temperate waters, shifted toward the equator, compressing the available habitat for warm-adapted organisms into an ever-shrinking band around the planet's middle. For millions of species, there was simply nowhere to go. They couldn't adapt quickly enough to the cold, and the warm zones they needed for survival were disappearing. The result was a biological catastrophe that unfolded in two devastating phases, each one demonstrating a different mechanism by which climate change can trigger mass extinction. The first phase coincided with the onset of glaciation and the dramatic sea level fall. This initial wave of extinction targeted organisms that lived in the disappearing shallow seas and those that couldn't tolerate the rapidly cooling temperatures. Entire groups of trilobites vanished. Many brachiopod families went extinct. The diverse communities that had flourished in the warm Ordovician seas were decimated. But just when it seemed like the surviving organisms might have a chance to adapt to the new cold world, Earth delivered a second punch that proved even more devastating. The ice sheets that had caused so much destruction began to melt, triggering the second phase of the extinction event. As glaciers retreated and temperatures rose, sea levels began to climb again. You might think this would be good news for marine life, a return to the conditions that had supported such diversity earlier in the Ordovician. But the environmental changes that accompanied this warming phase created an entirely different set of deadly conditions. The melting ice sheets and rising temperatures disrupted ocean circulation patterns in ways that proved catastrophic for marine ecosystems. As the seas warmed and circulation slowed, oxygen levels in many parts of the ocean began to drop dramatically. Large areas of the seafloor became anoxic, creating dead zones where nothing could survive. This ocean anoxia was particularly devastating because it affected the very organisms that had managed to survive the first phase of cooling and habitat loss. Species that had successfully adapted to the cold, changed ocean chemistry, and reduced habitat area suddenly found themselves facing suffocation in their own environment. The anoxic conditions were identified through careful analysis of uranium isotopes in rocks from the extinction boundary. These isotopic signatures revealed that about 15% of the seafloor became anoxic during the late Ordovician extinction, a massive increase in oxygen-depleted areas that lasted for at least 1 million years. What makes the Ordovician extinction particularly chilling is how it demonstrates that climate transitions themselves can become extinction mechanisms. It wasn't just the cold that killed, or just the warmth that followed. It was the transition between these states, the rapid environmental changes that left organisms with no stable conditions to which they could adapt. Many species that survived the initial cooling and sea level drop were completely unable to cope with the subsequent warming and chemical changes. This two-phase nature of the extinction created a double filter that eliminated organisms regardless of their specific environmental adaptations. Cold-adapted species died when conditions warmed, while any remaining warm-adapted species often couldn't cope with the anoxic conditions that developed during the warming phase. The late Ordovician extinction stands as proof that Earth doesn't need external catastrophes to eliminate most of its life. Simple changes in climate and ocean chemistry, driven entirely by the planet's own geological and atmospheric processes, can be just as deadly as any asteroid impact. In fact, in some ways they can be more deadly, because they can kill in multiple ways simultaneously and leave survivors with nowhere to hide. This glacial catastrophe also reveals something deeply unsettling about the relationship between life and climate. The very climate stability that allows complex ecosystems to flourish also makes them vulnerable to rapid change. The Ordovician biosphere had thrived for millions of years under warm, stable conditions. This success became its weakness when the climate shifted, because evolution had optimized these organisms for a world that suddenly no longer existed. The recovery from the Ordovician extinction took millions of years and resulted in completely reorganized marine ecosystems. Many groups that had dominated Ordovician seas never recovered their former diversity. New evolutionary lineages emerged to fill the empty ecological niches, but the ocean communities that eventually developed were fundamentally different from what had come before. This pattern of destruction and reorganization would become a recurring theme in Earth's history. Each mass extinction event didn't just remove species, it reset the evolutionary game board, creating opportunities for new groups to rise to prominence while ensuring that some lineages would never again achieve their former glory. But if the Ordovician extinction demonstrated how climate cooling could trigger mass death, our planet had even more creative methods of biological destruction waiting in its geological toolkit. The next chapter in Earth's catalogue of self-inflicted catastrophes would reveal how the protective systems that make life possible could themselves become instruments of extinction. The story moves forward through deep time to 359 million years ago, when Earth revealed yet another method of planetary homicide that scientists are only now beginning to understand. The End Devonian extinction event demonstrates something truly terrifying about our planet's capacity for destruction. Earth doesn't just kill with fire and ice. Sometimes it kills by destroying the very atmospheric shield that protects life from the cosmos. Picture the late Devonian world, a time when life had finally conquered the land in earnest. Vast forests of primitive trees stretched across the continents, creating Earth's first true woodland ecosystems. These weren't the forests we know today, but alien-looking landscapes dominated by towering lycopsid trees and early conifers that reached heights of 30 meters or more. The forest floor teemed with the first amphibians, creatures that were still learning how to live fully on land, while primitive insects buzzed through the humid air. In the oceans, armored fish ruled the waters. These placoderms, some growing to massive sizes, represented one of evolution's most successful experiments in vertebrate design. Their heavily armored heads and razor-sharp jaw plates made them the apex predators of their time. Alongside them swam early sharks and the first bony fish, groups that were just beginning their long journey toward dominance. But this thriving world was about to face something unprecedented in the history of life on Earth. Not volcanism, not climate change in the traditional sense, but the systematic destruction of the planet's ozone layer through entirely natural processes. What happened next would prove that Earth's atmospheric chemistry could become just as deadly as any geological catastrophe. The evidence for this atmospheric catastrophe comes from one of the most remarkable fossil discoveries in modern paleontology. In the remote landscapes of East Greenland, scientists found something that sent chills down the spine of anyone who understood its implications. Fossilized plant spores from the end Devonian period, preserved in exquisite detail, told a story of biological damage that could only have one cause. These ancient spores were malformed in very specific ways. Their cell walls showed the characteristic damage patterns that occur when developing plant reproductive cells are exposed to intense ultraviolet radiation. This wasn't random damage or the result of normal fossilization processes. This was the signature of DNA destruction caused by UVB radiation so intense that it overwhelmed the protective mechanisms that normally shield developing spores from radiation damage. The discovery was groundbreaking because it provided direct evidence that Earth's protective ozone layer had been severely compromised during the extinction event. Under normal circumstances, the ozone layer in the upper atmosphere absorbs most of the harmful ultraviolet radiation from the sun, allowing only relatively safe levels to reach the planet's surface. But something had gone catastrophically wrong with this protective system. What makes this discovery even more significant is what it reveals about the cause of the ozone depletion. Unlike other mass extinctions, there were no massive volcanic eruptions during the end Devonian event. Mercury concentrations in rocks from this period show no evidence of the large-scale volcanism that characterized other extinction events. The planet's usual suspect for atmospheric poisoning had an airtight alibi. Instead, the culprit appears to have been rapid climate warming following the end of a major ice age. The late Devonian period had been marked by intense glacial cycles, with ice sheets advancing and retreating across the southern continents. The final glaciation of this ice age ended abruptly, triggering a dramatic warming event that destabilized Earth's atmospheric chemistry in ways that scientists are only now beginning to understand. The mechanism behind this ozone destruction reveals something deeply unsettling about our planet's atmospheric systems. During rapid warming events, increased convective transport can carry chlorine-containing compounds high into the stratosphere, where they attack and break down ozone molecules. This isn't a freak accident or external interference. It's an inherent property of Earth's atmospheric system, a built-in vulnerability that can turn protective warming into a death trap. As the ozone layer thinned and eventually developed massive holes, deadly ultraviolet radiation began pouring down onto Earth's surface at levels that overwhelmed the protective mechanisms of most living organisms. The effects were swift and devastating, particularly for the complex forest ecosystems that had taken millions of years to develop. The malformed spores found in Greenland represent just the tip of the iceberg. These damaged reproductive cells indicate that entire plant communities were being sterilized by radiation levels that made reproduction impossible. Even if adult plants could survive the initial UV assault, they couldn't produce viable offspring. The result was a cascade of ecosystem collapse that began with the plants and worked its way up through every level of the food web. The structured forest communities that had dominated late Devonian landscapes simply disintegrated. The fossil record shows a complete loss of diversity across the extinction boundary, with at least 4 major spore groups that had thrived for millions of years vanishing entirely. The few plants that survived were predominantly small, simple species that could better tolerate the radiation assault. But the destruction didn't stop with the forests. As these complex plant communities collapsed, they triggered a cascade of environmental changes that amplified the catastrophe. Without the deep root systems and extensive canopy cover of the forests, soil erosion increased dramatically. Rain that had once been captured and slowly released by the forest ecosystem now rushed directly into rivers and streams, carrying massive loads of nutrients into the oceans. This sudden nutrient flush created a one-time pulse of oceanic productivity that further disrupted marine ecosystems. Algal blooms exploded across the continental shelves, consuming oxygen and creating dead zones in coastal waters. The increased biological activity also led to the production of methyl halogens, compounds that rose into the atmosphere and further attacked the already damaged ozone layer. The marine consequences were severe. The dominant group of armored fish, the placoderms that had ruled the oceans for millions of years, went extinct entirely. These heavily armored predators, some of which had grown to lengths of 10 meters or more, simply vanished from the fossil record. The extinction was so complete that not a single lineage survived into the following period. The survivors of this marine massacre were the sharks and bony fish, groups that remain dominant in modern oceans. But their survival came at a cost. The extinction occurred at a critical time in vertebrate evolution, just as the first tetrapods were making their tentative steps onto land. The collapse of terrestrial ecosystems and the disruption of marine food webs created enormous challenges for these early land vertebrates, potentially altering the entire trajectory of vertebrate evolution. What makes the end Devonian extinction particularly ominous for modern observers is how it demonstrates that atmospheric protection systems we take for granted can be destroyed by natural climate processes. The ozone layer isn't a permanent fixture of our planet. It's a dynamic system that can be disrupted by the same kinds of rapid warming events that are becoming increasingly common in our current era of climate change. The process that destroyed the Devonian ozone layer operates on a simple principle that remains true today. Rapid warming increases atmospheric convection, which can transport ozone-destroying compounds to altitudes where they can do maximum damage. Unlike the seasonal and geographically limited ozone depletion that occurs naturally, warming-induced ozone loss would be global and long-lasting, exactly the kind of atmospheric catastrophe that could trigger mass extinction. Some scientists have proposed that nearby supernova explosions might have contributed to the end Devonian ozone depletion, bombarding Earth with cosmic rays that could destroy atmospheric ozone. While this remains speculative, the discovery of UV-damaged fossils in Greenland provides a way to test such hypotheses. If cosmic rays were responsible, the damage patterns should be different from those caused by purely terrestrial atmospheric processes. But regardless of whether extraterrestrial factors played a role, the end Devonian extinction demonstrates that Earth's atmospheric systems contain built-in vulnerabilities that can turn protective mechanisms into instruments of destruction. The same convective processes that help regulate our planet's climate can, under the right conditions, destroy the atmospheric shields that make complex life possible. The recovery from this atmospheric catastrophe took millions of years and fundamentally changed the nature of terrestrial ecosystems. The complex, structured forests of the late Devonian were replaced by simpler plant communities, dominated by smaller, more radiation-tolerant species. It would be tens of millions of years before forests again achieved the complexity and diversity that had characterized the pre-extinction world. This extinction event also marked a turning point in the evolution of Earth's atmospheric chemistry. The planet's ozone layer eventually recovered, but the temporary loss of atmospheric protection served as a reminder that the chemical shields protecting life from cosmic radiation are more fragile than they appear. Earth had demonstrated yet another method of self-inflicted biological catastrophe, one that required no external assistance and left no obvious geological signature beyond the damaged remains of the organisms it killed. The Devonian extinction proves that sometimes the most dangerous threats to life come not from below the ground or from outer space, but from the invisible chemistry of the air itself. When Earth's protective systems fail, even briefly, the consequences can reshape the entire biosphere and alter the course of evolution for millions of years to come. But Earth's creativity in orchestrating biological disasters was far from exhausted. As the Devonian forests withered under lethal radiation and marine ecosystems collapsed, our planet was already preparing its next demonstration of geological violence. The stage was being set for another volcanic catastrophe that would prove volcanism remained one of Earth's most reliable methods of mass destruction. Destruction. Jump forward through the fossil record to 201 million years ago, and you'll encounter Earth's next masterpiece of destruction. The End-Triassic extinction event stands as proof that our planet never forgot how to wield volcanism as a weapon of mass destruction. But this time, the volcanic catastrophe would unfold with a precision and timing that seems almost calculated, as if Earth had learned from previous extinctions and refined its methods of biological annihilation. The late Triassic world was a time of evolutionary experimentation and recovery. Life had finally begun to bounce back from the devastation of the Great Dying, filling the ecological void left by the Permian catastrophe with new and innovative forms. Early dinosaurs shared the landscape with massive archosaurs. Primitive mammals scurried through the undergrowth, and the oceans teemed with marine reptiles that had evolved to exploit every available niche. But this recovering biosphere was about to face something that would make the Siberian traps look almost restrained by comparison. Deep beneath what would eventually become the Atlantic Ocean, geological forces were stirring that would create the most extensive volcanic province in Earth's history. The Central Atlantic Magmatic Province, known to scientists as CAMP, was preparing to unleash a volcanic catastrophe that would span multiple continents and eliminate 76% of all species on the planet. What made CAMP different from the Siberian traps wasn't just its size, though the scale was truly staggering. This volcanic province would eventually cover an area larger than the continental United States, stretching from what is now eastern North America through Europe and into Africa. But the real difference lay in the precision of its destruction, the almost surgical way it delivered environmental catastrophe in precisely timed pulses that gave life no chance to adapt or recover. Advanced geochronological techniques have revealed that CAMP eruptions occurred in 4 distinct pulses, each lasting no more than 100 years, but spread out over roughly 600,000 years. To understand the devastating efficiency of this timing, imagine a boxer delivering knockout punches with mathematical precision, allowing just enough time between blows for the victim to regain consciousness before delivering the next devastating hit. Each pulse of CAMP volcanism was a geological instant that pumped enormous quantities of carbon dioxide into the atmosphere with shocking speed. When scientists calculated the rate of carbon emissions during these volcanic bursts, they discovered something that should terrify anyone concerned about modern climate change. A single volcanic pulse from CAMP emitted roughly the same amount of carbon dioxide that human civilization is projected to release throughout the entire 21st century. But CAMP had advantages that even our modern industrial emissions can't match. While human carbon emissions come primarily from burning fossil fuels at relatively low temperatures, CAMP was releasing carbon through multiple mechanisms simultaneously. The volcanic eruptions themselves pumped out massive amounts of carbon dioxide directly from molten rock. But like the Siberian traps before it, CAMP had a secret weapon that amplified its destructive power beyond what simple volcanism could achieve. The magma wasn't just erupting onto empty rock surfaces. As it forced its way toward the surface, it encountered and burned through vast deposits of organic-rich sediments and coal seams. This created the same kind of feedback loop that had made the Siberian traps so deadly, with volcanic carbon emissions being amplified by the combustion of geological carbon stores that had been accumulating for millions of years. Recent research has revealed that camp volcanism also involved extensive intrusive activity, with magma forcing its way into sedimentary basins rich in organic matter. These intrusions occurred roughly 100,000 years before the earliest known surface eruptions, suggesting that the destruction began even before the visible volcanic activity started. When this subsurface magma encountered organic-rich rocks, it cooked off enormous quantities of greenhouse gases that began destabilizing Earth's climate system well before the main extinction event. The precision timing of these emissions created a cascade of environmental disasters that unfolded with terrifying efficiency. The first pulse of carbon dioxide triggered rapid global warming that disrupted weather patterns and began acidifying the oceans. Before life could adapt to these new conditions, the second pulse arrived, pushing atmospheric carbon dioxide levels even higher and creating environmental stresses that overwhelmed the adaptive capacity of most species. By the time camp reached its peak activity, atmospheric carbon dioxide levels had doubled, and in some cases tripled, compared to pre-extinction levels. Ocean temperatures rose dramatically, making vast areas of the seas uninhabitable for most marine life. The chemistry of seawater changed as it absorbed enormous quantities of carbon dioxide, creating acid conditions that dissolved the shells and skeletons of marine organisms. But camp delivered destruction through multiple pathways simultaneously, demonstrating a level of geological sophistication that seems almost malicious in its thoroughness. The initial phases of eruption released massive amounts of sulfur compounds along with carbon dioxide, creating intense volcanic winters that plunge global temperatures despite the ongoing greenhouse gas emissions. These temperature swings, from severe cooling to extreme warming sometimes within decades, created environmental whiplash that eliminated species regardless of their specific climate adaptations. The sulfur emissions during the early phases of camp activity were truly staggering in scale. Scientists estimate that these volcanic eruptions spewed more than 500 times the amount of sulfur released during the historic Laki eruption in Iceland, an event that caused climate disruption across the entire northern hemisphere. The resulting volcanic winters may have been the immediate cause of extinction in terrestrial environments, where sudden temperature drops eliminated entire ecosystems that had no experience with such rapid climate change. Meanwhile, in the marine realm, the longer-term effects of massive carbon dioxide emissions created a different but equally devastating set of killing mechanisms. Ocean acidification proceeded at rates that made adaptation impossible for most marine organisms. The warming seas lost their capacity to hold dissolved oxygen, creating vast anoxic dead zones where nothing could survive. Marine food webs collapsed as the foundation organisms, from plankton to coral reefs, succumbed to the combined assault of heat, acid, and oxygen depletion. The continental effects were equally severe but operated through different mechanisms. The collapse of marine ecosystems disrupted nutrient cycles that terrestrial life depended on. The extreme temperature swings eliminated plant communities, which in turn triggered cascading extinctions among herbivorous and carnivorous animals. Many terrestrial vertebrate groups that had survived previous extinction events, including several lineages of early archosaurs and primitive mammals, vanished entirely from the fossil record. What makes the end Triassic extinction particularly significant for understanding Earth's capacity for self-destruction is how it demonstrates the planet's ability to coordinate multiple killing mechanisms simultaneously. This wasn't just volcanism, or just climate change, or just ocean chemistry disruption. It was all of these things happening at once, creating a perfect storm of environmental catastrophe that attacked life from every possible angle. The recovery from this coordinated assault took millions of years and fundamentally reshaped the structure of terrestrial and marine ecosystems. The extinction eliminated many groups that had dominated Triassic environments, creating evolutionary opportunities that would be filled by entirely new lineages. Most significantly, for the future history of life on Earth, the end Triassic extinction eliminated many of the Archosaurian competitors of early dinosaurs, setting the stage for dinosaurian dominance that would last for over 150 million years. But perhaps the most unsettling aspect of the end Triassic extinction is what it reveals about the precision with which Earth's geological systems can orchestrate biological catastrophe. The timing of camp eruptions, the coordination of different volcanic processes, and the synchronization of multiple environmental killing mechanisms suggests that our planet's capacity for destruction operates according to principles that we are only beginning to understand. This level of geological coordination raises disturbing questions about other periods in Earth's history when volcanic activity, climate change, and ocean chemistry disruption might have worked together to create extinction events that we haven't yet recognized or fully understood. The end Triassic extinction proves that Earth doesn't need to rely on single catastrophic events to eliminate most of its life. It can orchestrate complex, multi-phase disasters that attack biological systems from every possible direction simultaneously. As camp finally began to subside and the immediate volcanic catastrophe ended, Earth's climate system remained unstable for hundreds of thousands of years. The massive quantities of carbon dioxide that had been pumped into the atmosphere continued to drive global warming and ocean acidification long after the eruptions ceased. This extended period of environmental stress prevented rapid biological recovery and ensured that the evolutionary consequences of the extinction would persist for millions of years. The end Triassic event also established a pattern that would become familiar in Earth's geological history. Major volcanic provinces don't just erupt and disappear. They leave behind environmental legacies that continue to shape planetary systems long after the visible volcanic activity has ended. The carbon dioxide emissions from camp continue to influence global climate for hundreds of thousands of years, creating a prolonged period of environmental instability that made biological recovery slow and difficult. This extended aftermath reveals another crucial aspect of how Earth orchestrates mass extinctions. The immediate volcanic catastrophe is often just the beginning. The real destruction comes from the long-term environmental changes that volcanic activity triggers, changes that can persist for geological ages and prevent ecosystems from recovering their former diversity and complexity. By the time the Earth's systems finally stabilized and began the long process of biological recovery, the planet had once again demonstrated its remarkable capacity for reinvention through destruction. The world that emerged from the end Triassic catastrophe was fundamentally different from what had come before, populated by new groups of organisms that would define the character of life for the next geological era. But even as life began to recover from this latest volcanic apocalypse, Earth's geological processes were already setting the stage for future demonstrations of planetary destructive power. The pattern was becoming clear. Our planet doesn't just experience occasional catastrophes. It operates according to cycles of destruction and renewal that have shaped the entire history of life. Cycles that continue to operate today with the same terrifying efficiency they displayed hundreds of millions of years ago. The story of Earth's capacity for self-inflicted biological destruction was far from over. Each extinction event had revealed new mechanisms, new ways that planetary processes could turn against the very life they normally supported. And as we'll discover, the creativity of geological destruction had not yet reached its limits. Earth still had more lessons to teach about the fragility of life and the awesome power of planetary forces that operate entirely independently of any cosmic intervention. These volcanic catastrophes, from the Siberian traps through camp, established volcanism as one of Earth's most reliable methods of biological destruction. but they also revealed something more subtle and perhaps more disturbing about our planet's relationship with life. The timing, scale, and coordination of these volcanic events suggests that Earth's geological systems possess an almost purposeful efficiency when it comes to eliminating biological diversity. This efficiency extends beyond simple volcanic activity to encompass complex interactions between atmospheric chemistry, ocean circulation, climate systems, and biological processes. Each major extinction event has revealed new connections between these systems, new ways that disruptions in one area can cascade through the entire planetary biosphere to create destruction on a global scale. The pattern that emerges from studying these ancient catastrophes is both fascinating and terrifying. Earth doesn't just kill randomly or accidentally. It kills systematically, using multiple coordinated mechanisms that ensure maximum biological impact with minimal geological effort. The planet has perfected the art of mass destruction over hundreds of millions of years, refining its techniques through repeated practice until it can eliminate most of life with surgical precision. This realization forces us to confront an uncomfortable truth about our relationship with the planet we call home. Earth is not a stable, benevolent provider that exists solely to support life. It is a dynamic, sometimes hostile system that has repeatedly demonstrated its willingness and ability to eliminate most of the life it has produced. The volcanic extinctions of the Permian and Triassic periods serve as stark reminders that our planet's capacity for destruction operates on scales and timescales that dwarf human comprehension. Understanding these ancient catastrophes becomes even more critical when we consider that the geological processes responsible for past mass extinctions remain active today. Large igneous provinces continue to form. Volcanic activity continues to release greenhouse gases into the atmosphere, and the complex interactions between geological and biological systems continue to operate according to the same principles that drove past extinction events. The volcanic catastrophes of Earth's past serve as both warning and prophecy, demonstrating that our planet's most devastating extinction events require no assistance from outer space. They are homegrown disasters, born from the very geological processes that make Earth a living, dynamic world. And as we'll discover, volcanism represents just one method in Earth's extensive toolkit of biological destruction. Our planet has many other ways to eliminate life, methods that operate through entirely different mechanisms, but with equally devastating results. Devastating results. As we journey deeper into Earth's catalogue of self-inflicted catastrophes, we encounter extinction mechanisms that operate through pathways so subtle they remained hidden from scientists for decades. These aren't the obvious devastation of massive volcanic eruptions or the dramatic cooling of ice ages. These are the quiet killers, the invisible assassins that work through the very chemistry of life itself. Picture the ancient oceans of 420 million years ago, during what geologists call the Silurian period. These seas sparkled under a sun that looked much the same as today, supporting vast coral reefs and complex marine ecosystems that had recovered from earlier extinction events. Fish were beginning to diversify into the groups that would eventually colonize every corner of the planet's waters. Early plants were taking their first tentative steps onto land, creating the foundation for terrestrial ecosystems that would support all future land life. But beneath the seemingly peaceful surface of these ancient oceans, something sinister was stirring. The very chemistry that made life possible was beginning to turn toxic, initiating a process that would demonstrate yet another method by which Earth could orchestrate biological catastrophe without any external assistance whatsoever. Ocean anoxia represents one of Earth's most insidious killing mechanisms because it attacks the fundamental process that powers complex life. Every breath you take, every heartbeat that pumps oxygenated blood through your body, depends on the availability of dissolved oxygen in the environment where life evolved. When that oxygen disappears, even temporarily, the results are swift and merciless. During the Silurian extinction event, researchers have uncovered evidence that vast areas of the ocean floor became completely anoxic, creating underwater dead zones where nothing could survive. This wasn't a gradual process that gave organisms time to adapt. Advanced analysis of uranium isotopes in rocks from this period reveals that approximately 15% of the seafloor suddenly became oxygen depleted, a massive increase that lasted for over 1 million years. The mechanism behind this oceanic suffocation reveals how Earth's interconnected systems can amplify relatively small changes into planetary catastrophes. As global temperatures rose due to increased volcanic carbon dioxide emissions, the ocean's capacity to hold dissolved oxygen decreased dramatically. Warm water simply cannot contain as much oxygen as cold water, a basic principle of chemistry that becomes a death sentence when applied on a planetary scale. But the warming alone wasn't sufficient to create the massive anoxic zones that characterized this extinction event. The real killer emerged from the complex interactions between rising sea levels, nutrient runoff from the continents, and the biological processes that should have been supporting marine life. As ice sheets melted and sea levels rose, vast areas of previously dry land became flooded, bringing nutrient-rich waters into contact with continental shelves that had been exposed for millions of years. These nutrients, primarily nitrogen and phosphorus that had accumulated in soils and sediments, suddenly found themselves dissolved in seawater, where they triggered massive algal blooms across the continental margins. At first glance, this explosion of marine productivity might seem like good news for ocean ecosystems. More algae should mean more food for filter-feeding organisms, more oxygen production through photosynthesis, and more robust food webs supporting diverse marine communities. But the reality proved to be exactly the opposite, demonstrating how Earth's biological systems can become instruments of their own destruction. The algal blooms were so massive and so widespread that they consumed enormous quantities of nutrients, creating a boom and bust cycle that devastated marine ecosystems. When the algae died and sank to the ocean floor, their decomposition consumed vast amounts of dissolved oxygen from the water column. The bacteria responsible for breaking down this organic matter literally suffocated the ocean from the bottom up, creating expanding zones of anoxic water that rose toward the surface like an underwater plague. The effects were catastrophic for marine life. Bottom-dwelling organisms were the first to die as anoxic conditions spread across the seafloor. But as the oxygen-depleted water rose higher in the water column, it began affecting organisms throughout the marine ecosystem. Fish that had ruled these ancient seas for millions of years found themselves trapped in an environment that could no longer support their basic metabolic needs. What makes ocean anoxia particularly devastating as an extinction mechanism is its persistence. Unlike volcanic eruptions that eventually end, or climate changes that can reverse over time, anoxic ocean conditions can persist for hundreds of thousands or even millions of years. The bacterial processes that consume oxygen operate continuously as long as organic matter continues to rain down from the surface waters, creating a feedback loop that maintains deadly conditions long after the initial trigger has disappeared. Recent research has revealed that ocean anoxia wasn't limited to the Silurian extinction. Advanced geochemical analysis has found evidence of widespread oxygen depletion associated with each of the big 5 mass extinctions, suggesting that oceanic suffocation represents one of Earth's most reliable methods of biological destruction. From the Great Dying of the Permian through the end Cretaceous asteroid impact, every major extinction event shows evidence of significant ocean anoxia. This pattern reveals something deeply disturbing about the relationship between Earth's climate system and its capacity to support life. The same warming processes that can make the planet more habitable in some regions simultaneously make vast areas of the ocean uninhabitable for complex organisms. It's a planetary balancing act, where the margin for error is measured in degrees of temperature change that seem insignificant until they trigger cascading environmental failures. The mechanisms that create ocean anoxia operate according to principles that remain active in modern oceans. Current climate change is already reducing oxygen levels in many parts of the world's seas, creating expanding dead zones that mirror the conditions responsible for ancient mass extinctions. The difference is that we can now observe these processes in real time, watching as the same chemical and biological mechanisms that drove past extinctions begin to operate in our contemporary oceans. But ocean anoxia represents just one pathway through which Earth's marine systems can turn deadly. The planet's capacity for oceanic destruction extends far beyond simple oxygen depletion to encompass chemical changes that can poison entire ocean basins and transform life-supporting seas into toxic wastelands. The chemistry of ancient oceans during extinction events reveals a level of environmental hostility that challenges our understanding of what conditions can support complex life. During the Permian extinction, for example, the seas didn't just lose their oxygen. They became actively poisonous, filled with hydrogen sulfide and other toxic compounds that made survival impossible for most marine organisms. These toxic conditions developed through the same bacterial processes that created ocean anoxia, but under circumstances so extreme that they produced entirely different and more deadly results. When anoxic conditions became severe enough, different types of bacteria took over the decomposition process, producing hydrogen sulfide instead of consuming oxygen. This created oceans that didn't just lack the chemistry necessary for life, but actively poisoned anything that tried to survive in them. The evidence for these toxic ocean conditions comes from chemical signatures preserved in rocks that formed during extinction events. Isotopic analysis reveals the presence of compounds that could only have been produced by bacteria operating under extremely anoxic conditions. Bacteria that produce some of the most toxic substances known to biology. Hydrogen sulfide, in particular, represents a chemical nightmare for complex life. This compound, which gives rotten eggs their characteristic smell, is deadly to most organisms even in relatively small concentrations. When entire ocean basins became filled with hydrogen sulfide-producing bacteria, they transformed from life-supporting environments into vast toxic lakes that could kill anything that ventured into them. The persistence of these toxic conditions helps explain why recovery from major extinction events took so long. It wasn't just a matter of waiting for temperatures to return to normal or for sea levels to stabilize. Entire ocean basins had to be flushed clean of toxic compounds and repopulated with the bacterial communities necessary to support complex life. This process required millions of years and fundamentally changed the chemistry of Earth's oceans. Understanding these ancient toxic oceans becomes particularly relevant when we consider how modern climate change is affecting ocean chemistry. Current warming trends are already creating conditions that favor the same types of bacterial processes that produced toxic oceans during past extinction events. While we're not yet seeing hydrogen sulfide production on a planetary scale, the chemical pathways that could lead to such conditions are becoming increasingly active in warming ocean basins around the world. The study of ancient ocean chemistry also reveals how seemingly small changes in marine environments can trigger cascading failures that affect the entire planetary biosphere. The initial warming that triggered ocean anoxia during the Silurian extinction was relatively modest by geological standards, perhaps only a few degrees of temperature increase. But this small change set in motion a series of chemical and biological processes that ultimately transformed the entire character of marine ecosystems. This sensitivity of ocean chemistry to relatively small environmental changes demonstrates why marine extinction events can develop so rapidly and with such devastating consequences. The ocean systems that support complex life operate within narrow chemical parameters, and when those parameters are exceeded, the results can be swift and irreversible on timescales relevant to most species. The interconnected nature of ocean chemistry also means that problems in one part of the marine system can quickly spread to affect the entire global ocean. Anoxic conditions that develop in coastal areas can expand to cover vast areas of the deep ocean. Toxic bacterial blooms that begin in isolated basins can spread through ocean currents to poison marine ecosystems thousands of kilometers away. These ancient oceanic catastrophes reveal that Earth's marine systems possess their own capacity for self-destruction that operates independently of any terrestrial or cosmic influences. The oceans don't need volcanic eruptions or asteroid impacts to become uninhabitable. They can poison themselves through entirely natural biological and chemical processes that turn life-supporting environments into toxic wastelands. The implications of this oceanic capacity for self-destruction extend far beyond understanding ancient extinctions. Modern oceans are experiencing chemical changes that mirror many of the conditions associated with past extinction events. Rising temperatures, increasing acidity, and expanding oxygen-depleted zones all represent early stages of the same processes that created oceanic catastrophes in Earth's past. But the ocean's capacity for destruction extends beyond chemistry to encompass physical changes that can eliminate marine habitats on continental scales. Sea level changes, driven by climate shifts and geological processes, have repeatedly drained and refilled entire ocean basins, creating extinction events through simple habitat destruction. The power of sea level change as an extinction mechanism becomes clear when we consider that most marine life exists in the shallow seas that cover continental shelves and margins. These epicontinental seas represent some of the most biologically productive environments on Earth, supporting dense concentrations of marine organisms in relatively small volumes of water. When sea levels drop even modestly, these crucial habitats can disappear entirely, taking their entire ecosystems with them. During the Ordovician extinction, sea level drops of approximately 100 meters eliminated vast areas of shallow marine habitat across the globe. To understand the scale of this habitat loss, imagine every coastal ecosystem on Earth today suddenly finding itself stranded high and dry, with no deeper water refuges available for the organisms that had evolved specifically for shallow water conditions. The speed at which these habitat changes could occur adds to their destructive power. Geological evidence suggests that major sea level changes during extinction events happened over periods of thousands to tens of thousands of years. Timescales that seem long to human observers but represent geological instants that gave marine ecosystems no time to adapt or migrate to surviving habitats. Recovery from habitat destruction through sea level change often required millions of years, not because the physical environment couldn't return to previous conditions, but because the complex ecosystems that had been eliminated took enormous amounts of time to re-evolve. Many groups of organisms that lost their habitats to sea level change never recovered their former diversity, leaving permanent gaps in marine ecosystems that persist to this day. The study of ancient sea level changes reveals that Earth's marine systems are far more fragile than they appear. The vast oceans that seem so permanent and unchanging from human perspectives are actually dynamic systems that can be dramatically altered by geological and climate processes operating on timescales that dwarf individual lifespans, but represent mere moments in Earth's long history. These oceanic extinction mechanisms demonstrate that Earth's capacity for biological destruction extends far beyond the dramatic volcanic catastrophes that capture most public attention. The quiet killers that operate through ocean chemistry and sea level change can be just as effective at eliminating life as any massive eruption or asteroid impact. They reveal a planet where the very environments that support life can become instruments of death through entirely natural processes. The precision with which these oceanic killing mechanisms operate suggests that Earth's marine systems have been refined over billions of years into efficient agents of both creation and destruction. The same chemical and physical processes that make the oceans incredibly productive. Environments for life can, under slightly different conditions, transform them into biological wastelands where nothing can survive. Understanding these oceanic extinction mechanisms becomes crucial as we observe similar processes beginning to operate in modern seas. The chemical signatures that characterized ancient toxic oceans are starting to appear in contemporary marine environments. The habitat destruction that eliminated shallow marine ecosystems during past sea level changes is beginning to affect modern coastal environments as climate change alters precipitation patterns and ice sheet stability. The ancient oceans serve as both laboratory and warning, demonstrating the full range of ways that marine environments can turn hostile to life. They remind us that the seas that seem so vast and stable from human perspectives are actually delicate systems operating within narrow parameters that, when exceeded, can trigger catastrophic changes affecting the entire planetary biosphere. But perhaps most unsettling of all, the study of ancient oceanic extinctions reveals that these marine-killing mechanisms often work in coordination with terrestrial processes to create planet-wide catastrophes that attack life from multiple directions simultaneously. The same climate changes that trigger ocean anoxia can also destabilize atmospheric chemistry, while the same geological processes that cause sea level changes can trigger massive volcanic eruptions. This coordination between different extinction mechanisms suggests that Earth's capacity for biological destruction operates according to principles we are only beginning to understand. The planet doesn't just eliminate life randomly or through isolated catastrophes. It orchestrates complex, multi-system disasters that ensure maximum biological impact through the coordinated failure of multiple environmental systems. As we trace the history of these oceanic catastrophes through deep time, a pattern emerges that is both fascinating and terrifying in its implications. Earth's marine systems don't just support life. They serve as testing grounds where the planet experiments with different methods of biological destruction, refining its techniques over hundreds of millions of years until it achieves maximum efficiency in eliminating complex ecosystems. The oceans that seem so peaceful and life-supporting from our limited human perspective are actually dynamic arenas where the fundamental chemistry of life is constantly being tested against the planet's capacity for environmental extremism. Most of the time, life wins these contests, adapting and thriving despite constant chemical and physical challenges. But periodically, the planet's destructive capacity overwhelms biological adaptability, creating extinction events that reshape the entire character of marine life. These oceanic killing mechanisms represent some of Earth's most subtle but effective methods of biological destruction, proving that our planet doesn't need dramatic volcanic fireworks or cosmic catastrophes to eliminate most of its life. Sometimes the most devastating extinctions happen quietly, through chemical changes so gradual they're barely perceptible until they reach tipping points where entire marine ecosystems collapse almost instantaneously. The ancient seas serve as a reminder that stability is an illusion when viewed from the perspective of geological time. The marine environments that support most of Earth's biological diversity exist within narrow chemical and physical parameters that can be disrupted by relatively small changes in global environmental conditions. When those parameters are exceeded, the results can be swift, devastating, and irreversible on timescales relevant to complex life. But the ocean's role in Earth's extinction events extends beyond serving as a victim of environmental change. Marine systems also serve as amplifiers, taking relatively small environmental perturbations and magnifying them into global catastrophes through complex feedback mechanisms that can persist for millions of years. The seas don't just respond to extinction events. They actively participate in creating and sustaining the conditions that make biological recovery slow and difficult. This active role of marine systems in extinction events reveals another layer of Earth's capacity for self-inflicted biological destruction. The planet doesn't just eliminate life through isolated catastrophes that eventually end, allowing recovery to begin. It creates self-sustaining cycles of environmental hostility that can persist long after the initial triggering events have ceased. ensuring that extinction events have lasting consequences that reshape the entire trajectory of evolutionary history. The recovery from these oceanic catastrophes reveals another disturbing truth about Earth's relationship with life. Our planet doesn't just eliminate biological diversity and then passively wait for new species to evolve. It actively shapes the conditions under which recovery occurs, often in ways that ensure the new biosphere will be fundamentally different from what came before. During the millions of years required for marine ecosystems to recover from major extinction events, Earth's geological and chemical systems continue to operate according to their own rhythms, creating environmental conditions that favor entirely different types of organisms than those that dominated pre-extinction ecosystems. The planet essentially redesigns itself during these recovery periods, establishing new rules for what kinds of life can survive and thrive. This process of environmental redesign helps explain why post-extinction biotas often look so different from their predecessors. It's not just that certain groups went extinct and were replaced by others. The entire environmental framework within which life operates gets restructured during major extinction events, creating selective pressures that favor completely different evolutionary strategies and ecological relationships. The fossil record reveals that these post-extinction worlds often remained unstable for millions of years after the immediate catastrophe ended. Climate systems stayed erratic, ocean chemistry remained volatile, and sea levels continued to fluctuate unpredictably. Life during these recovery periods had to evolve under conditions of constant environmental uncertainty, which favored organisms with broad tolerances and flexible survival strategies over those specialized for stable conditions. This extended environmental instability serves as another mechanism through which Earth prevents rapid biological recovery. Just as ecosystems begin to re-establish themselves, new environmental shocks eliminate recently evolved species and reset the evolutionary clock. The planet seems to actively resist the re-establishment of complex, stable ecosystems for millions of years after major extinction events. But Earth's capacity for biological destruction extends beyond the marine realm and the dramatic volcanic catastrophes we've already explored. Some of the planet's most effective extinction mechanisms operate through terrestrial processes that can eliminate entire continental biotas without leaving obvious geological signatures. These land-based killing mechanisms demonstrate that Earth's creativity in orchestrating biological destruction is truly boundless. Consider the role of continental configuration in driving extinction events. As the planet's crustal plates drift across the surface over millions of years, they periodically collide to form supercontinents, massive landmasses that fundamentally alter global climate patterns and create entirely new environmental challenges for terrestrial life. The formation of supercontinents represents one of Earth's most subtle but effective long-term extinction mechanisms. When continents collide and merge into single massive landmasses, they create continental interiors so vast that normal weather patterns cannot penetrate to their centers. These continental heartlands become increasingly arid and hostile to life, creating enormous deserts where diverse ecosystems once flourished. The process operates on timescales so long that it's almost invisible to normal geological observation, but its effects are devastating for continental biotas. As supercontinents form, vast areas of previously habitable land become uninhabitable, forcing surviving organisms into ever-shrinking refugia around continental margins. The result is a gradual but inexorable compression of terrestrial biodiversity that can persist for tens of millions of years. During the late Permian period, the formation of the supercontinent Pangaea created exactly these conditions. The continental interior became a vast, hyper-arid wasteland where temperatures could exceed 50 degrees Celsius, and rainfall was virtually non-existent. The few organisms that could survive in these conditions were highly specialized desert species with little ecological diversity. This continental aridification worked in concert with the Siberian Traps volcanism to amplify the devastation of the Great Dying. While volcanic emissions poisoned the atmosphere and oceans, the hostile continental climate eliminated most terrestrial refugia where land animals might have survived the environmental catastrophe. The planet had coordinated its geological processes to attack life from both sea and land simultaneously. But supercontinent formation also triggers extinction through more direct mechanisms. The massive mountain-building events that occur when continents collide alter atmospheric circulation patterns on a global scale, disrupting monsoon systems and changing precipitation patterns across entire hemispheres. Ecosystems that had evolved under specific climate regimes suddenly find themselves facing entirely different environmental conditions, with no opportunity to migrate to more suitable habitats. The collision of continents also affects global sea level through several mechanisms. The formation of massive mountain ranges removes enormous quantities of water from the oceans as it gets incorporated into rock formations. Continental collisions can also alter the volume of ocean basins, causing sea levels to rise or fall dramatically over relatively short geological periods. These tectonically driven sea level changes create extinction pressures that operate independently of climate change or volcanic activity. When colliding continents reduce ocean basin volume, rising seas flood vast areas of previously dry land, eliminating terrestrial habitats and creating environmental refugees with nowhere to go. Conversely, when tectonic activity increases ocean basin capacity, falling sea levels eliminate the shallow marine habitats that support most oceanic biodiversity. The timing of these tectonic extinction mechanisms often coincides with other planetary catastrophes, creating compound disasters that are far more devastating than any single environmental crisis could be. The formation of Pangaea during the late Permian coincided almost exactly with the Siberian Traps eruptions, while major continental collisions during other periods have aligned with massive volcanic episodes and rapid climate changes. This coordination between tectonic and volcanic processes isn't coincidental. The same deep Earth dynamics that drive continental drift also control the formation of large igneous provinces and the timing of massive volcanic eruptions. When continents collide, they create conditions in the deep mantle that favor the formation of enormous magma chambers, setting the stage for volcanic catastrophes that can persist for hundreds of thousands of years. The study of these coordinated tectonic and volcanic events reveals that Earth's most devastating extinction episodes often result from the synchronization of multiple geological processes. The planet doesn't just rely on single catastrophic events to eliminate life. It orchestrates complex geological symphonies where different Earth systems work together to maximize biological destruction. This coordination extends to timescales that dwarf human comprehension. The geological processes that drive major extinction events operate over millions of years, building toward catastrophic crescendos with a patience and precision that seems almost purposeful. Continental collisions, mantle dynamics, and volcanic activity all follow rhythms that occasionally align to create perfect storms of environmental destruction. Understanding these long-term geological cycles becomes crucial for recognizing that Earth's capacity for biological destruction operates according to predictable principles. The planet has been refining its extinction mechanisms for billions of years, developing increasingly sophisticated methods for eliminating complex life whenever it becomes too successful or too stable. The terrestrial extinction mechanisms also demonstrate how environmental changes can cascade through ecosystems in ways that amplify relatively small initial perturbations into global catastrophes. The aridification of continental interiors during supercontinent formation begins as a subtle shift in precipitation patterns, but it eventually eliminates entire biomes and forces complete reorganization of terrestrial ecosystems. These cascading environmental failures help explain why recovery from major extinction events takes so long, and why post-extinction biotas are so different from their predecessors. It's not just that certain species go extinct and need to be replaced. The entire environmental framework that supported pre-extinction ecosystems gets dismantled and rebuilt according to new rules that favor completely different types of organisms. The role of continental configuration in driving extinction also reveals how Earth's most devastating biological catastrophes can unfold without any obvious geological signatures. Unlike massive volcanic eruptions or asteroid impacts that leave clear evidence in the rock record, continental aridification and climate reorganization operate through subtle environmental changes that are difficult to detect millions of years after they occur. This subtlety makes terrestrial extinction mechanisms particularly dangerous because they can eliminate vast amounts of biodiversity without triggering the dramatic environmental changes that might allow some organisms to recognize the threat and adapt accordingly. By the time the full scope of continental environmental degradation becomes apparent, most terrestrial ecosystems have already passed the point of no return. The study of ancient continental configurations also reveals that Earth's current geography represents just one temporary arrangement in an ongoing process of crustal reorganization. The continents are currently moving toward new collision zones that will eventually create another supercontinent, triggering the same aridification and climate disruption processes that have driven terrestrial extinctions in the past. Modern climate change is accelerating some of these terrestrial extinction mechanisms by increasing the rate of continental interior aridification and disrupting precipitation patterns that support existing terrestrial ecosystems. While we're not currently experiencing continental collision, we are witnessing the same types of environmental cascades that have driven major extinction events in Earth's past. The terrestrial realm also demonstrates how Earth can eliminate life through biological processes that operate independently of geological catastrophes. Ecosystem collapse can occur through entirely biological mechanisms when environmental changes disrupt the complex relationships between species that support diverse biological communities. During several extinction events, the elimination of key species triggered cascading failures that brought down entire ecosystems, even in areas where environmental conditions remained relatively stable. The loss of major plant groups during the end Devonian extinction, for example, eliminated the foundation species that supported complex terrestrial food webs, causing the collapse of animal communities that might otherwise have survived the environmental changes. These biological cascades demonstrate that Earth doesn't always need dramatic environmental catastrophes to eliminate large numbers of species. Sometimes the planet can achieve mass extinction through subtle disruptions to ecological relationships, causing biological communities to collapse from within rather than being destroyed by external environmental forces. The precision with which these biological extinction mechanisms operate suggests that Earth's ecosystems contain built-in vulnerabilities that can be exploited by relatively small environmental perturbations. Complex biological communities that seem robust and stable from short-term perspectives often depend on delicate balances between species that can be disrupted by changes so subtle they're barely detectable until the ecosystem collapse is already underway. Understanding these biological extinction mechanisms becomes particularly important for recognizing how modern environmental changes might trigger ecosystem collapses that parallel those seen during ancient extinction events. Current biodiversity loss is already disrupting ecological relationships in ways that mirror the biological cascades responsible for some of Earth's most devastating extinction episodes. The terrestrial extinction record also reveals that Earth's capacity for biological destruction extends to the elimination of entire evolutionary innovations that had taken millions of years to develop. Complex adaptations that represented major evolutionary breakthroughs have been eliminated repeatedly throughout Earth's history, forcing evolution to restart from simpler organizational levels. The Permian extinction eliminated most of the complex terrestrial vertebrate communities that had evolved during the Permian period, including many groups that had developed sophisticated adaptations for life on land. The recovery from this terrestrial catastrophe required the re-evolution of complex social behaviors, advanced physiological adaptations, and ecological relationships that had been completely eliminated by the environmental crisis. This pattern of evolutionary reset demonstrates that Earth's extinction mechanisms don't just eliminate individual species or even families of organisms. They can erase entire chapters of evolutionary history, forcing life to rediscover solutions to environmental challenges that had already been solved by earlier evolutionary lineages. The repeated elimination of evolutionary innovations helps explain why biological complexity has increased so slowly over Earth's history, despite the enormous creative potential of evolutionary processes. Every time life develops sophisticated solutions to environmental challenges, planetary catastrophes eliminate these innovations and force evolution to begin again from simpler starting points. This cycle of evolutionary progress and reset reveals another layer of Earth's relationship with biological complexity. The planet seems to actively resist the accumulation of sophisticated biological innovations, periodically eliminating the most advanced forms of life and creating opportunities for entirely different evolutionary experiments to take their place. The terrestrial extinction record also demonstrates how Earth can eliminate life through the disruption of physical habitats rather than chemical or climate changes. Massive erosion events triggered by the elimination of plant communities during extinction crises can physically destroy the soil and sediment layers that support terrestrial ecosystems. During several major extinction events, the collapse of vegetation cover led to unprecedented erosion rates that literally stripped away the substrate on which terrestrial life depends. Rivers and streams became choked with sediment from eroding landscapes, while coastal areas were buried under enormous quantities of debris washed down from barren continental interiors. These physical habitat destruction events can persist for hundreds of thousands of years after the initial extinction crisis ends, preventing rapid biological recovery and ensuring that post-extinction landscapes remain hostile to complex life for extended periods. The planet essentially strips away the physical foundation for terrestrial ecosystems, forcing any surviving organisms to rebuild not just biological communities, but the very habitats in which those communities exist. The role of erosion in prolonging extinction events reveals another mechanism through which Earth ensures that biological recovery remains slow and difficult. Even if environmental conditions return to normal relatively quickly after a major extinction event, the physical destruction of terrestrial habitats can prevent ecosystem re-establishment for millions of years. Understanding these physical habitat destruction mechanisms becomes crucial for recognizing how modern environmental changes might trigger similar processes. Current deforestation and soil degradation are already accelerating erosion rates in many parts of the world, creating conditions that mirror the habitat destruction events associated with ancient extinction crises. The terrestrial extinction mechanisms also reveal how Earth can eliminate life through the disruption of nutrient cycles that support biological productivity. Major extinction events often coincide with the breakdown of the complex biogeochemical processes that cycle essential nutrients through ecosystems, creating biological deserts even in areas where climate conditions remain suitable for life. The collapse of nutrient cycling during extinction events occurs through multiple pathways. The elimination of key plant and animal species disrupts the biological processes that move nutrients between different ecosystem compartments. Soil microbe communities that mediate essential chemical transformations can be eliminated by environmental changes, breaking the links between geological and biological nutrient sources. When nutrient cycles collapse, even surviving organisms often cannot maintain viable populations because the chemical foundation for biological productivity has been eliminated. Ecosystems can become nutrient-limited deserts where primary productivity is so low that complex food webs cannot be sustained, regardless of other environmental conditions. The recovery of nutrient cycling after major extinction events requires the re-evolution of complex biological and chemical relationships that can take millions of years to re-establish. The planet must essentially rebuild the biogeochemical machinery that supports life, a process that involves coordinating biological evolution with geological processes operating on entirely different timescales. These nutrient cycle disruptions demonstrate that Earth's extinction mechanisms operate at the most fundamental levels of biological organization. The planet doesn't just eliminate individual species or ecosystems, it can dismantle the very chemical processes that make life possible, forcing complete reconstruction of the biogeochemical systems that support biological productivity. As we trace these terrestrial extinction mechanisms through Earth's history, a comprehensive picture emerges of our planet's remarkable capacity for biological destruction. Earth possesses an extensive toolkit of extinction mechanisms that can operate individually or in coordination to eliminate life at scales ranging from local ecosystems to global biotas. The diversity and sophistication of these extinction mechanisms reveal that our planet has been experimenting with biological destruction for billions of years, refining its techniques through repeated practice until it can eliminate complex life with surgical precision. From massive volcanic catastrophes to subtle disruptions of nutrient cycles, Earth has developed methods for attacking life from every possible angle. But perhaps most unsettling of all, the study of terrestrial extinction mechanisms reveals that these destructive processes remain active in the modern world. The same geological, climatic, and biological processes that drove ancient extinction events continue to operate today, creating the potential for similar catastrophes in our contemporary biosphere. The coordination between different extinction mechanisms also suggests that Earth's capacity for biological destruction operates according to principles that transcend individual catastrophic events. The planet seems to possess an inherent tendency toward periodic biological reset, using whatever mechanisms are available to eliminate complex life whenever it becomes too successful or too stable. This pattern of coordinated destruction and renewal has shaped the entire history of life on Earth, creating the boom and bust cycles that characterize biological evolution over geological timescales. Understanding these cycles becomes crucial for recognizing that extinction isn't an aberration in Earth's history. It's a fundamental feature of how our planet operates as a biological system. The terrestrial extinction record serves as both a catalogue of past catastrophes and a guide to understanding the mechanisms that continue to shape biological diversity in the modern world. Every major extinction event has left lessons about the vulnerabilities inherent in complex biological systems and the remarkable efficiency with which Earth can exploit those vulnerabilities to reshape the entire character of life. As we witness accelerating environmental changes in our contemporary world, the ancient terrestrial extinctions serve as both warning and prophecy, demonstrating the full range of ways that planetary processes can turn against the very life they normally support. The creativity and precision of Earth's biological destruction mechanisms remind us that our planet's capacity for catastrophe operates on scales and through pathways that continue to challenge our understanding of what makes complex life possible. The terrestrial extinction mechanisms reveal that Earth's relationship with biological complexity is far more dynamic and potentially hostile than it appears from human perspectives. The solid ground beneath our feet and the stable ecosystems that surround us exist within a planetary system that has repeatedly demonstrated its willingness and ability to eliminate most of the life it has produced. But the story of Earth's self-inflicted biological catastrophes extends beyond individual extinction mechanisms to encompass the larger patterns and cycles that govern the planet's long-term relationship with life. Understanding these patterns becomes crucial for recognizing that mass extinctions aren't random accidents, but predictable features of how Earth operates as a geological and biological system. The timing of major extinction events reveals underlying rhythms in Earth's geological processes that suggest our planet's capacity for destruction operates according to cycles that span tens of millions of years. These cycles appear to be driven by deep Earth dynamics that coordinate surface processes with mantle convection and core evolution, creating periodic episodes when multiple extinction mechanisms align to create perfect storms of environmental catastrophe. These cycles reveal themselves through patterns in the geological record that span hundreds of millions of years, creating a rhythm of destruction and renewal that appears to be as fundamental to Earth's operation as the rotation of its core or the drift of its continents. When scientists began mapping the timing of major extinction events across deep time, they discovered something both fascinating and deeply unsettling about the regularity with which our planet eliminates most of its life. The spacing between major extinction events isn't random. Statistical analysis reveals periodicities that suggest underlying geological processes operate on predictable timescales, creating windows of vulnerability when Earth's biological systems become susceptible to catastrophic failure. These windows appear to open roughly every 26 to 30 million years, though the exact timing varies depending on the complex interactions between different planetary systems. What drives these cycles of destruction remains one of the most intriguing questions in Earth science. Some researchers point to oscillations in the planet's orbit around the galactic center, suggesting that our solar system's movement through different regions of space might trigger periodic increases in cosmic ray bombardment or gravitational disturbances that affect Earth's geological stability. Others focus on internal planetary processes, particularly the cycles of mantle convection, that drive plate tectonics and volcanic activity. Deep within Earth, massive convection cells transport heat from the core toward the surface over periods of tens of millions of years. When these convection patterns shift or intensify, they can trigger coordinated episodes of volcanic activity, continental drift, and climate change that create ideal conditions for mass extinction. The relationship between mantle dynamics and extinction timing becomes particularly clear when examining the formation of large igneous provinces. These massive volcanic events don't occur randomly throughout Earth's history, but cluster into periods of intense activity separated by long intervals of relative calm. The clustering suggests that deep Earth processes periodically reach critical thresholds where enormous quantities of magma are generated simultaneously across multiple regions of the planet. During these periods of enhanced mantle activity, Earth becomes a fundamentally more dangerous place for complex life. Multiple volcanic provinces can erupt simultaneously, pumping unprecedented quantities of greenhouse gases into the atmosphere while triggering climate changes that affect every corner of the planet. The coordination between different volcanic systems during these episodes suggests that Earth's interior operates according to rhythms that periodically synchronize to create maximum surface disruption. But the cycles of extinction and recovery also reveal something remarkable about life's resilience in the face of planetary catastrophe. Despite experiencing 5 major extinction events that eliminated between 70 and 96% of all species, life has not only survived, but repeatedly bounced back to achieve even greater complexity and diversity than existed before the catastrophe. This pattern of recovery and diversification following extinction events suggests that mass death paradoxically serves as a creative force in evolution. By eliminating dominant species and disrupting established ecological relationships, extinction events create evolutionary opportunities that would never exist under stable environmental conditions. The empty niches left by extinct organisms become laboratories for evolutionary experimentation, allowing surviving lineages to explore entirely new ways of living and interacting with their environment. The recovery from the end Permian extinction provides perhaps the most dramatic example of this evolutionary creativity. The few vertebrate lineages that survived the Great Dying found themselves in a world with virtually no competition and enormous numbers of vacant ecological niches. This unprecedented evolutionary opportunity led to an explosion of biological innovation that produced entirely new groups of organisms, including the archosaurs that would eventually give rise to dinosaurs, crocodiles, and birds. Similarly, the end Cretaceous extinction that eliminated non-avian dinosaurs created evolutionary opportunities that mammals had never possessed during the Mesozoic era. Within just a few million years of the extinction event, mammals diversified from small generalized forms into an incredible array of specialized species that filled ecological roles previously occupied by dinosaurs. This rapid evolutionary radiation produced most of the major mammalian lineages that dominate modern terrestrial ecosystems. The speed and scope of post-extinction evolutionary radiations reveal that life possesses remarkable latent potential for diversification that can only be unleashed when existing biological hierarchies are disrupted. Under normal ecological conditions, established species and ecosystems create competitive pressures that limit opportunities for major evolutionary innovation. Extinction events temporarily remove these constraints, allowing evolution to explore possibilities that would be impossible under stable conditions. But the recovery process also demonstrates the profound challenges that life faces when attempting to rebuild complex ecosystems from the devastated remnants left by mass extinction. The fossil record shows that full ecosystem recovery typically requires 5 to 10 million years, with some aspects of biological complexity taking even longer to re-establish. During the early phases of recovery, ecosystems remain simple and unstable, dominated by opportunistic species with broad environmental tolerances and rapid reproductive rates. These pioneer communities lack the complex interactions and specialized relationships that characterize mature ecosystems, making them vulnerable to additional environmental disturbances that can reset the recovery process. The gradual rebuilding of ecosystem complexity follows predictable patterns that reveal fundamental principles about how biological communities assemble themselves after catastrophic disruption. Primary producers, the plants and other photosynthetic organisms that form the base of food webs, typically recover first, establishing the foundation for more complex biological relationships. Herbivorous organisms follow, taking advantage of the expanding plant communities, but often remaining relatively generalized in their feeding habits until plant diversity increases sufficiently to support specialized relationships. Carnivorous species appear last in the recovery sequence, requiring established populations of prey species before they can maintain viable populations. This stepwise recovery process explains why ecosystem reconstruction takes so much longer than simple species replacement. It's not enough for new species to evolve to fill vacant niches. These species must also develop the complex ecological relationships that bind biological communities together into stable, self-regulating systems. The development of these ecological relationships often requires coevolutionary processes where different species adapt to each other over hundreds of thousands or millions of years. Predator-prey relationships, mutualistic partnerships, and competitive interactions all require fine-tuning through evolutionary feedback that can only occur over extended time periods. During this extended recovery phase, ecosystems remain vulnerable to additional disturbances that can derail the reconstruction process and force biological communities to begin rebuilding from even simpler starting points. The geological record shows numerous examples of interrupted recoveries where secondary environmental crises eliminated newly evolved biological communities before they could achieve stability. These interrupted recoveries reveal another layer of Earth's relationship with biological complexity. The planet doesn't just eliminate complex life through major extinction events and then passively allow recovery to proceed. It continues to test recovering ecosystems with smaller environmental challenges that serve as filters, allowing only the most robust biological communities to achieve long-term stability. This ongoing environmental testing helps explain why post-extinction biotas often possess different characteristics than their predecessors. Ecosystems that develop under conditions of environmental uncertainty tend to favor different evolutionary strategies than those that evolve under stable conditions. The result is that recovered ecosystems, while often more diverse than their predecessors, operate according to different ecological principles. The fossil record reveals that these differences between pre- and post-extinction ecosystems can persist for tens of millions of years, creating distinct evolutionary eras separated by mass extinction boundaries. Each major extinction event essentially creates a new chapter in the history of life, with different groups of organisms assuming dominant roles and different ecological strategies proving most successful. This pattern of ecosystem replacement rather than simple recovery demonstrates that mass extinctions don't just eliminate biodiversity temporarily. They permanently alter the trajectory of biological evolution, ensuring that life's history consists of a series of distinct episodes rather than gradual, continuous change. The profound changes in ecosystem structure that follow major extinctions also affect the planet's biogeochemical cycles in ways that can influence environmental stability for millions of years. Different types of organisms process nutrients, produce waste products, and modify their physical environment in different ways. When extinction events replace one biological community with another, they can fundamentally alter how ecosystems interact with atmospheric and oceanic chemistry. These biogeochemical changes can create feedback loops that either enhance or reduce environmental stability during the recovery period. In some cases, newly evolved biological communities develop more efficient nutrient cycling or more effective carbon storage, creating environmental conditions that support greater biological diversity. In other cases, the loss of key functional groups can destabilize biogeochemical cycles in ways that make environments less suitable for complex life. The long-term effects of these biogeochemical changes help explain why some extinction events are followed by periods of exceptional biological diversification, while others lead to extended intervals of ecosystem simplification. The biological communities that emerge from extinction events don't just fill empty ecological niches. They actively reshape the environmental conditions that determine what kinds of life can survive and thrive. Understanding these biogeochemical feedbacks becomes crucial for recognizing that extinction and recovery represent coupled processes where biological and environmental change influence each other over millions of years. The planet's capacity for destruction is matched by an equally remarkable capacity for biological creativity, but the two processes operate according to different timescales and principles that can either complement or conflict with each other. The study of extinction and recovery cycles also reveals that Earth's biological systems possess multiple stable states, with major extinction events serving as transitions between different planetary configurations. Each post-extinction world represents a fundamentally different experiment in biological organization, with different groups of organisms assuming control over essential ecosystem functions. These alternative stable states help explain why recovery from mass extinction involves more than simple replacement of extinct species. The biological communities that emerge from extinction events often organize themselves according to entirely different principles, creating ecosystems that would be impossible under the environmental conditions that supported pre-extinction life. The transition between these stable states appears to involve threshold effects, where relatively small environmental changes can trigger cascading biological reorganization that affects the entire planetary biosphere. Once these transitions begin, they tend to continue until completely new biological equilibria are established, regardless of whether environmental conditions return to pre-extinction norms. This threshold behavior suggests that Earth's biological systems possess built-in instabilities that can be triggered by environmental perturbations below the level that would seem necessary to cause global ecosystem collapse. The planet appears to exist in a constant state of metastable equilibrium, where biological communities can be toppled by disturbances that seem modest compared to their ultimate effects. The recognition of these biological thresholds has profound implications for understanding how modern environmental changes might affect contemporary ecosystems. Current biodiversity loss and environmental modification may be pushing Earth's biological systems toward threshold transitions that could trigger cascading changes comparable to those seen during ancient mass extinctions. The ancient cycles of extinction and recovery also demonstrate that Earth's capacity for biological destruction operates within larger patterns of planetary evolution that span billions of years. The methods and mechanisms that drive extinction events have themselves evolved over geological time, becoming more sophisticated and efficient as Earth's geological and atmospheric systems have matured. Early extinction events in Earth's history operated through relatively simple mechanisms, primarily involving changes in atmospheric composition or ocean chemistry. But as the planet's systems became more complex and interconnected, extinction mechanisms evolved to exploit these new complexities, developing the ability to trigger cascading failures across multiple environmental systems simultaneously. This evolution of extinction mechanisms suggests that Earth's capacity for biological destruction is not fixed, but continues to develop new capabilities as planetary systems become more sophisticated. The same evolutionary processes that increase biological complexity also create new vulnerabilities that can be exploited by extinction mechanisms operating at planetary scales. The implications of this ongoing evolution of destructive capacity extend to understanding how Earth might eliminate complex life in the future. The mechanisms that drove past extinction events may represent only a fraction of the destructive potential that our planet could develop as its geological, atmospheric, and biological systems continue to evolve. But the cycles of extinction and recovery also reveal something hopeful about life's relationship with planetary catastrophe. Despite facing repeated episodes of near-total elimination, life has consistently demonstrated an ability not just to survive, but to achieve greater complexity and diversity than existed before each catastrophic event. This pattern suggests that biological systems possess inherent creative potential that can only be fully realized under the extreme selective pressures created by mass extinction events. The elimination of established biological hierarchies appears to be necessary for unlocking evolutionary possibilities that remain dormant under normal ecological conditions. The repeated recovery and diversification of life following mass extinctions also demonstrates that biological creativity operates on timescales that dwarf individual catastrophic events. While extinction events can eliminate most life in geological instants, the creative response of biological systems unfolds over millions of years, ultimately producing levels of complexity and diversity that exceed anything that existed before the catastrophe. This temporal asymmetry between destruction and creation reveals a fundamental principle about Earth's relationship with life. The planet's capacity for elimination operates through rapid, coordinated processes that can reshape entire biospheres in thousands or tens of thousands of years. But biological creativity requires extended periods of environmental stability and evolutionary experimentation that can only occur over millions of years. The tension between these different timescales creates the boom and bust cycles that characterize life's history on Earth. Periods of biological diversification and ecosystem development are periodically interrupted by rapid extinction events that eliminate accumulated biological complexity and force life to begin the creative process again from simpler starting points. Understanding these cycles becomes crucial for recognizing that mass extinction represents a fundamental feature of how Earth operates as a biological system rather than an aberration that threatens the normal functioning of planetary life. The planet has been eliminating and recreating complex biological systems for billions of years, suggesting that this cycle of destruction and renewal serves essential functions in the long-term evolution of life. The ancient history of extinction and recovery also provides perspective on the current biodiversity crisis that many scientists believe represents the beginning of a sixth mass extinction driven by human activities. While the mechanisms involved in this modern extinction differ from those that drove ancient catastrophes, the underlying patterns of biological vulnerability and ecosystem collapse show remarkable similarities to past events. Current species loss rates exceed background extinction levels by factors of hundreds to thousands, approaching the rates seen during the most severe extinction events in Earth's history. The mechanisms driving modern extinctions, including habitat destruction, climate change, and ecosystem fragmentation, mirror many of the processes that eliminated biodiversity during ancient catastrophes. But the modern extinction also possesses unique characteristics that distinguish it from previous events in Earth's history. For the first time, a single species, humans, is driving extinction processes that affect every major ecosystem on the planet simultaneously. This represents a fundamentally new type of extinction mechanism that operates through biological rather than geological processes. The speed at which human-driven extinction is proceeding also exceeds most ancient catastrophes, with significant biodiversity loss occurring over decades rather than thousands or tens of thousands of years. This compression of extinction timescales may not allow the gradual ecosystem adjustments that helped some species survive previous extinction events. Yet the ancient history of extinction and recovery also suggests reasons for cautious optimism about life's long-term prospects. Earth's biological systems have survived catastrophes far more severe than anything currently occurring, including events that eliminated over 90% of all species. The creative potential that allowed life to recover from these ancient disasters remains active in modern biological systems. The mechanisms that drive post-extinction evolutionary radiation continue to operate in contemporary ecosystems, ready to exploit the ecological opportunities that would be created if current extinction pressures were reduced. Modern biological systems possess the same fundamental capacity for diversification and innovation that allowed life to recover from ancient catastrophes. Understanding the ancient cycles of extinction and recovery provides crucial insights into the timescales and processes that would be involved in biological recovery from modern extinction pressures. While ecosystem reconstruction would require millions of years, the potential for renewed biological creativity remains inherent in Earth's evolutionary systems. The study of ancient extinctions also reveals that recovery processes can be accelerated or enhanced by environmental conditions that promote biological innovation and ecosystem development. Creating such conditions could help modern biological systems begin the recovery process even while current extinction pressures continue to operate. But perhaps most importantly, the ancient history of extinction and recovery demonstrates that Earth's capacity for biological destruction, while formidable, is ultimately limited by the same planetary processes that make life possible. The geological and atmospheric systems that can eliminate complex life also create the environmental conditions necessary for biological recovery and diversification. This fundamental coupling between destructive and creative planetary processes suggests that Earth's long-term trajectory involves continued cycles of biological elimination and renewal rather than permanent sterility. The planet possesses both the capacity to eliminate most of its life and the environmental conditions necessary for biological systems to recover and achieve even greater complexity. The ancient extinction events serve as reminders that life's relationship with Earth involves constant negotiation between biological creativity and planetary destructive capacity. Understanding this relationship becomes crucial for recognizing that current environmental challenges, while severe, represent part of an ongoing dialogue between life and planet that has shaped biological evolution for billions of years. The cycles of extinction and recovery reveal that Earth's history consists not of steady biological progress, but of repeated experiments in biological organization, each one testing different solutions to the fundamental challenges of living on a dynamic, sometimes hostile planet. Each extinction event eliminates one set of solutions and creates opportunities for entirely new approaches to biological organization. This experimental nature of life's history suggests that current biological diversity represents just one possible solution to the challenges of living on Earth. The extinction events of the past eliminated countless alternative solutions, while future extinctions will likely test the viability of current biological arrangements and create opportunities for innovations that are currently impossible to imagine. The profound creativity revealed by post-extinction evolutionary radiations also suggests that life's potential for complexity and diversity far exceeds what has been realized at any single point in Earth's history. Each extinction event eliminates certain possibilities, but creates opportunities for others, ensuring that biological evolution continues to explore new organizational strategies over geological time. Understanding this ongoing exploration becomes crucial for appreciating that extinction events, while devastating for existing biological communities, serve essential functions in the long-term development of a life's complexity and diversity. The elimination of established biological hierarchies appears to be necessary for accessing evolutionary possibilities that remain dormant under stable conditions. The ancient cycles of destruction and renewal reveal that Earth's relationship with life operates according to principles that transcend individual catastrophic events or evolutionary innovations. The planet serves as both destroyer and creator, eliminating biological complexity when it becomes too rigid or specialized, while creating conditions that promote new forms of biological organization. This dual nature of Earth's relationship with life helps explain the remarkable persistence and creativity of biological systems over billions of years. The same planetary processes that threaten life's existence also drive the innovation and diversification that allow biological systems to achieve ever greater complexity and environmental mastery. The study of extinction and recovery cycles also reveals that life's history on Earth represents an ongoing conversation between biological and planetary evolution, with each influencing the other over timescales that span millions to billions of years. Understanding this conversation becomes crucial for recognizing that current environmental challenges represent part of a much larger dialogue that will continue to shape life's future, regardless of the specific outcomes of contemporary extinction pressures. As we trace these ancient patterns of destruction and renewal through deep time, we begin to understand that Earth's capacity for eliminating complex life represents just one aspect of a planetary system that has been experimenting with biological organization for over 3 billion years. The same creative forces that allow life to recover from mass extinctions continue to operate in modern biological systems, ready to respond to current challenges with the same innovative potential that has characterized life's response to planetary catastrophe throughout Earth's long history. The ancient extinctions remind us that while Earth's capacity for biological destruction is truly formidable, it is ultimately overshadowed by an even more remarkable capacity for biological creativity that has allowed life not just to survive but to flourish in the face of repeated planetary catastrophes. This creative potential represents our planet's most profound and enduring characteristic, ensuring that the story of life on Earth will continue to unfold in ways that challenge our understanding of what is possible in the ongoing dialogue between life and the dynamic planet that serves as both its greatest threat and its most essential partner. The ancient patterns of destruction and renewal that we've traced through Earth's deep history reveal something both terrifying and magnificent about our planet's relationship with life. But these cycles also force us to confront a disturbing question that challenges everything we thought we knew about our place in the cosmic order. If Earth has been systematically eliminating complex life for hundreds of millions of years, what does that mean for the future of biological diversity on our planet? The answer lies in understanding that extinction and evolution operate as paired processes, locked in an eternal dance that has shaped every aspect of life's development. Each major extinction event doesn't just eliminate species randomly, it selectively removes certain types of biological organization while creating opportunities for entirely different evolutionary experiments to take center stage. Consider what happened to body size evolution following major extinction events. Time and again, the fossil record shows that large, complex organisms are disproportionately affected by environmental catastrophes. Giant marine reptiles vanish from the oceans. Massive terrestrial vertebrates disappear from the continents. Complex reef ecosystems built by large organisms collapse entirely. But this selective elimination of large, complex life forms serves a crucial evolutionary function. During stable periods, these dominant organisms monopolize resources and ecological niches, preventing smaller, more innovative lineages from exploring new evolutionary possibilities. When extinction events remove these biological gatekeepers, they unleash waves of evolutionary experimentation that would be impossible under normal conditions. The mammals that inherited the Earth after the dinosaur extinction provide a perfect example of this process in action. For over 100 million years, mammals remained small, generalized creatures living in the shadows of reptilian giants. Their evolutionary potential was constrained not by any inherent limitations, but by the ecological dominance of dinosaurs that occupied every major terrestrial niche. When the end Cretaceous extinction eliminated non-avian dinosaurs, mammals suddenly found themselves in a world with virtually unlimited evolutionary opportunities. Within just 10 million years, they had diversified into forms ranging from tiny shrews to massive ground sloths, from aquatic whales to flying bats. This explosive radiation produced more mammalian diversity than had accumulated during the entire previous history of the group. The speed and scope of this post-extinction diversification reveals something profound about evolution's creative potential. The genetic and developmental systems that allowed mammals to achieve such rapid diversification had been present throughout the Mesozoic era, but they remained dormant under the competitive pressures created by dinosaur dominance. Extinction didn't create new evolutionary capabilities. It simply removed the ecological constraints that had prevented those capabilities from being expressed. This pattern of constrained evolution, followed by explosive diversification, appears throughout the fossil record, suggesting that biological systems routinely possess far more creative potential than they can express under normal ecological conditions. Major extinction events serve as evolutionary reset buttons that allow life to access this latent creativity and explore biological possibilities that would otherwise remain forever unrealized. But the relationship between extinction and evolutionary innovation operates through mechanisms far more subtle than simple competitive release. Major environmental catastrophes also alter the fundamental rules that govern biological success, changing the selective pressures that determine which evolutionary strategies prove most effective. During the Permian extinction, for example, the environmental changes that eliminated most marine life also transformed the ocean chemistry in ways that favored entirely different types of organisms. The acidic, low oxygen conditions that killed off most Paleozoic marine groups created opportunities for new lineages that possessed biochemical adaptations for surviving in hostile chemical environments. The organisms that emerged from this chemical apocalypse weren't just different species filling the same ecological roles as their predecessors. They represented fundamentally new approaches to marine life, with novel physiological systems that allowed them to thrive in environmental conditions that would have been lethal to pre-extinction biotas. This pattern of physiological innovation following extinction events demonstrates that environmental catastrophes don't just rearrange existing biological diversity. They drive the evolution of entirely new biological capabilities that expand the range of environmental conditions in which complex life can exist. The development of these new physiological systems often requires the coordinated evolution of multiple biochemical pathways, a process that typically takes millions of years under normal conditions. But the extreme selective pressures created by mass extinction can accelerate this process dramatically, compressing millions of years of gradual physiological evolution into hundreds of thousands of years of rapid adaptive change. The result is that post-extinction biotas often possess biological capabilities that far exceed those of their predecessors. Life doesn't just recover from mass extinctions, it emerges from them with enhanced abilities to survive future environmental challenges. Each major extinction event essentially upgrades Earth's biological systems, creating more robust and adaptable forms of life. But this enhancement comes at an enormous cost in terms of lost biological diversity and ecosystem complexity. The sophisticated ecological relationships that took millions of years to develop get eliminated in geological instants, while the enhanced biological capabilities that emerge from extinction events require equally long periods to reach full expression. This temporal asymmetry between biological destruction and reconstruction creates the boom and bust cycles that characterize life's history on Earth. Periods of gradual ecosystem development and increasing biological complexity are punctuated by rapid extinction events that eliminate accumulated diversity but set the stage for even greater future complexity. Understanding these cycles becomes crucial for recognizing that biological complexity doesn't increase steadily over time. Instead, it develops through a series of discrete jumps separated by catastrophic setbacks, with each jump potentially exceeding the complexity that existed before the preceding extinction event. The fossil record reveals that this pattern of punctuated complexity increase has accelerated over geological time, with post-extinction recoveries achieving greater diversity and sophistication than previous recoveries. This suggests that Earth's biological systems are becoming more efficient at translating extinction-driven opportunities into evolutionary innovations. But the mechanisms that drive this increasing efficiency remain poorly understood. Some researchers point to the accumulation of genetic and developmental tools that make rapid evolutionary change more feasible. Others focus on the increasing connectivity between different biological systems that allows innovations in one group to trigger cascading changes throughout entire ecosystems. The role of genetic and developmental evolution in shaping extinction and recovery patterns reveals another layer of complexity in Earth's biological cycles. The organisms that survive major extinction events don't just fill empty ecological niches. They also inherit the genetic legacy of all the lineages that went extinct, in the form of conserved developmental pathways and biochemical systems. This genetic inheritance means that post-extinction evolutionary radiations can access biological innovations that were developed by extinct lineages, allowing rapid reconstruction of complex biological capabilities that might otherwise take millions of years to re-evolve from scratch. Extinction events eliminate species and ecosystems, but they preserve the underlying genetic and developmental infrastructure that makes complex life possible. The preservation of this biological infrastructure helps explain why recovery from mass extinction can proceed so rapidly once environmental conditions stabilize. The fundamental biochemical and developmental systems that support complex life remain intact even when most species are eliminated, providing a foundation for rapid biological reconstruction. But this genetic legacy also constrains the directions that post-extinction evolution can take. While extinction events create opportunities for biological innovation, they don't eliminate the developmental and physiological constraints that channel evolutionary change along certain pathways. The result is that post-extinction biotas often show surprising similarities to their predecessors, despite developing under completely different environmental conditions. These evolutionary constraints help explain why certain types of biological organization appear repeatedly throughout Earth's history, even after being eliminated by major extinction events. The genetic and developmental systems that produce these organizational patterns persist across extinction boundaries, ensuring their eventual reappearance whenever environmental conditions permit. The interplay between evolutionary opportunity and constraint during post-extinction recovery reveals that biological systems possess a kind of memory that transcends individual extinction events. While species and ecosystems can be eliminated, the deeper organizational principles that govern biological complexity persist and reassert themselves during subsequent evolutionary radiations. This biological memory helps explain the remarkable consistency in certain ecological patterns across different geological eras. Despite experiencing repeated mass extinctions that eliminated most species, Earth's ecosystems consistently redevelop similar organizational structures, from the basic architecture of food webs to the complex relationships between predators and prey. The persistence of these organizational patterns suggests that there are fundamental principles governing biological organization that remain constant despite dramatic changes in species composition and environmental conditions. Understanding these principles becomes crucial for predicting how modern ecosystems might reorganize themselves in response to current extinction pressures. But the study of ancient extinction and recovery cycles also reveals that biological memory has limits. Certain types of biological organization, once eliminated by mass extinction, never reappear in subsequent evolutionary radiations. These lost organizational patterns represent evolutionary experiments that exceeded the bounds of biological memory, taking forms so specialized or unusual that they couldn't be reconstructed from the genetic and developmental infrastructure that survived extinction events. The permanent loss of certain biological innovations during extinction events demonstrates that not all evolutionary achievements are recoverable. Some advances in biological complexity represent unique solutions to environmental challenges that, once eliminated, cannot be rediscovered through subsequent evolutionary processes. This irreversible loss of biological innovations adds another dimension to the cost of mass extinction events. Beyond the immediate elimination of species and ecosystems, extinction events permanently reduce the total range of biological possibilities that life has explored, closing off evolutionary pathways that might have led to even greater complexity and diversity. The accumulation of these permanent losses over geological time suggests that Earth's biological systems face a fundamental trade-off between current diversity and long-term evolutionary potential. Each extinction event enhances the adaptability and robustness of surviving lineages, while simultaneously eliminating unique biological innovations that can never be recovered. Understanding this trade-off becomes crucial for evaluating the long-term consequences of current extinction pressures. While modern biological systems retain the capacity for evolutionary innovation and recovery, the permanent loss of unique species and biological relationships occurring today will constrain the possibilities available to future evolutionary radiations. The ancient patterns of extinction and recovery also reveal that Earth's biological systems operate within broader cosmic cycles that influence the frequency and severity of extinction events over very long timescales. The planet's orbit around the galactic center exposes it to different cosmic environments that can affect the stability of its climate and geological systems. During periods when the solar system passes through regions of space with higher concentrations of cosmic rays or gravitational disturbances, Earth experiences increased rates of climate change and geological activity that create conditions favoring mass extinction. These cosmic cycles operate on timescales of hundreds of millions of years, creating meta-patterns in extinction frequency that transcend individual geological processes. The recognition of these cosmic influences on extinction patterns suggests that Earth's biological systems must contend not only with planetary-scale catastrophes, but also with disturbances originating from the broader galactic environment. This cosmic context adds another layer of complexity to understanding the long-term dynamics of extinction and recovery. But even within these cosmic constraints, Earth's biological systems have demonstrated remarkable persistence and creativity over billions of years. The same planetary processes that drive extinction events also create the environmental conditions necessary for life to recover and achieve even greater complexity. This fundamental coupling between destruction and creation appears to be an inherent feature of how life operates on a dynamic planet. The ancient cycles of extinction and recovery ultimately reveal that Earth's relationship with life transcends simple concepts of destruction or creation. Our planet serves as both the greatest threat to biological complexity and the essential foundation that makes that complexity possible. Understanding this paradoxical relationship becomes crucial for appreciating the remarkable persistence of life in the face of repeated planetary catastrophes. As we trace these patterns through deep time, we begin to understand that the extinction events we've explored represent just the most dramatic episodes in an ongoing dialogue between life and planet that has shaped biological evolution for over 3 billion years. This dialogue continues today, with current environmental changes representing the latest chapter in a story that spans geological ages. The mechanisms that drove ancient extinctions remain active in the modern world, creating the potential for similar catastrophes in our contemporary biosphere. But the creative potential that allowed life to recover from past disasters also persists, ready to respond to current challenges with the same innovative capacity that has characterized biological systems throughout Earth's history. The ancient extinctions serve as both warning and promise, demonstrating the fragility of individual species and ecosystems while revealing the remarkable resilience and creativity of life as a planetary phenomenon. They remind us that while Earth's capacity for biological destruction is truly formidable, it operates within a larger system that has consistently favored the persistence and diversification of complex life over geological time. Understanding these deep patterns becomes essential as we face the challenges of our current environmental crisis. The same principles that governed ancient cycles of extinction and recovery continue to operate today, offering insights into both the threats facing modern biological systems and the mechanisms through which those systems might respond to contemporary challenges. The story of Earth's self-inflicted biological catastrophes ultimately reveals that our planet's relationship with life involves constant negotiation between destructive and creative forces that have shaped biological evolution for billions of years. This negotiation continues today, ensuring that the future of life on Earth will be determined by the same dynamic interactions between geological, climatic, and biological processes that have driven the cycles of destruction and renewal we've traced through deep time. The ancient extinctions prove that Earth doesn't need cosmic catastrophes to reshape the entire character of life. Our planet possesses its own remarkable capacity for biological destruction, refined through billions of years of geological evolution into mechanisms that can eliminate most complex life with surgical precision. But these same mechanisms also create the conditions necessary for life to achieve even greater complexity and diversity than existed before each catastrophic event. This paradox lies at the heart of understanding Earth's relationship with life. The planet that can eliminate 96% of all species in a geological instant is the same planet that provides the environmental foundation for biological recovery and innovation. The geological processes that drive mass extinction also create the conditions that make post-extinction evolutionary radiations possible. As we witness accelerating environmental changes in our modern world, the ancient cycles of extinction and recovery provide crucial perspective on the challenges facing contemporary biological systems. While current extinction pressures operate through mechanisms different from those that drove ancient catastrophes, the underlying patterns of biological vulnerability and resilience show remarkable consistency across geological time. The creative potential that allowed life to recover from ancient disasters remains active in modern biological systems, ready to respond to current challenges with innovations that we cannot yet imagine. Understanding this potential becomes crucial for recognizing that while our planet's capacity for biological destruction is truly formidable, it is ultimately overshadowed by an even more remarkable capacity for biological creativity that has ensured life's persistence through every catastrophe Earth has produced. The ancient extinctions remind us that life's relationship with our dynamic planet involves constant adaptation to environmental challenges that operate on scales from local ecosystems to global biotas. This relationship has persisted for billions of years and will continue to shape biological evolution, regardless of the specific outcomes of contemporary environmental changes. In the end, the story of Earth's self-inflicted biological catastrophes reveals that our planet's most profound characteristic is not its capacity for destruction, but its remarkable ability to transform destruction into creativity, ensuring that the dialogue between life and planet continues to generate new forms of biological organization that push the boundaries of what is possible in our corner of the universe. But even as we marvel at life's remarkable capacity for recovery and reinvention, we must confront a sobering reality about our own place in this ancient cycle of destruction and renewal. Modern humans represent something unprecedented in Earth's 4.5 billion year history. For the first time, a single species has developed the technological capability to trigger extinction mechanisms that rival the planet's own geological processes in their speed and scope. The current biodiversity crisis unfolds with a velocity that exceeds most ancient catastrophes. While the Siberian traps took hundreds of thousands of years to eliminate 96% of life, human activities are driving species extinct at rates that compress similar levels of biological destruction into mere centuries. We've essentially accelerated Earth's natural extinction mechanisms, creating what many scientists now recognize as the sixth mass extinction event. Yet the mechanisms driving this modern catastrophe operate through pathways that would be familiar to any organism that survived ancient extinction events. Habitat destruction mirrors the sea level changes that eliminated shallow marine ecosystems during the Ordovician extinction. Climate change driven by greenhouse gas emissions parallels the atmospheric disruption that characterized the Permian and Triassic catastrophes. Ocean acidification recreates the toxic marine chemistry that poisoned ancient seas. But there's a crucial difference that makes the current extinction uniquely dangerous. Unlike geological processes that operate with cosmic patience, human-driven environmental change compresses multiple extinction mechanisms into overlapping timeframes that give biological systems no opportunity to adapt. We're simultaneously altering climate, destroying habitats, poisoning ecosystems, and fragmenting populations at rates that overwhelm evolution's capacity to respond. The fossil record suggests that biological systems can survive individual catastrophes, even severe ones, if they're given sufficient time between major environmental disruptions. The key to long-term survival appears to be the spacing between extinction pressures, which allows populations to recover and ecosystems to restabilize before facing the next challenge. Modern environmental change eliminates this crucial recovery time, creating a sustained assault on biological systems that has no precedent in Earth's history. Consider the compound nature of current environmental stresses. Rising temperatures stress organisms that are simultaneously losing their habitats to development, while ocean acidification affects marine life already struggling with pollution and overfishing. These multiple, simultaneous pressures create synergistic effects that can trigger ecosystem collapses, even when individual stressors remain below lethal thresholds. This multiplicative impact of concurrent environmental changes mirrors the coordinated destruction that characterized Earth's most severe extinction events. The difference is that ancient catastrophes typically involved the synchronization of geological processes operating over thousands of years. Modern extinction involves the synchronization of human activities operating over decades, compressing similar levels of environmental disruption into timeframes that challenge the very concept of biological adaptation. The speed of current change also affects the types of organisms most likely to survive. Ancient extinction events typically favored species with broad environmental tolerances, rapid reproductive rates, and generalized ecological requirements. Modern extinction pressures select for similar characteristics, but the compressed timeframes involved may exceed the adaptive capacity even of traditionally resilient organisms. Small population sizes become particularly problematic under rapid environmental change. While large populations can maintain genetic diversity and weather moderate environmental fluctuations, smaller populations lack the genetic resources necessary to adapt quickly to rapidly changing conditions. Modern habitat fragmentation has reduced most species to precisely these vulnerable small populations, creating a global biological system that's primed for cascading failure. The interconnected nature of modern ecosystems also amplifies extinction risks in ways that ancient biological systems never experienced. Global trade networks can spread diseases and invasive species across continents in days rather than the millennia required for natural dispersal. Climate change can eliminate species habitats faster then they can migrate to suitable areas. Pollution can accumulate in food webs until it reaches toxic concentrations in organisms thousands of miles from its source. These modern connectivity effects create the potential for synchronized ecosystem collapses across multiple continents simultaneously. While ancient extinction events typically spread from epicenters over thousands of years, giving distant ecosystems time to develop responses to approaching environmental changes. Modern extinction mechanisms can affect every corner of the planet nearly instantaneously. Yet understanding Earth's ancient capacity for biological destruction also provides crucial insights into the mechanisms that might allow modern ecosystems to survive current environmental challenges. The same principles that governed ancient extinctions and recoveries continue to operate today, offering both warnings about current vulnerabilities and guidance for enhancing biological resilience. The fossil record reveals that survival during mass extinction events depends on certain key characteristics that remain relevant for modern conservation efforts. Geographic distribution proves crucial, with species occupying multiple, isolated habitats showing higher survival rates than those restricted to single regions. Ecological flexibility allows organisms to exploit new food sources or habitats when their preferred environments become unavailable. Physiological tolerance for environmental variation enables species to survive the dramatic conditions that characterize extinction events. As we reach the end of our journey through Earth's catalogue of self-inflicted catastrophes, one truth emerges with crystal clarity. Our planet doesn't need cosmic assistance to eliminate most of life. From the toxic seas of the Permian to the radiation-scorched landscapes of the Devonian, Earth has demonstrated time and again that it possesses its own terrifying capacity for biological destruction. Yet within this story of repeated annihilation lies something even more remarkable: the unwavering persistence of life itself, rising from each catastrophe more complex and resilient than before. Tonight, we've seen that mass extinction isn't Earth's greatest achievement. Its greatest achievement is the endless creativity that transforms each ending into a new beginning.